Good morning, everybody. Welcome to another Builder Forum series. We'll give it, say, another 30 seconds or so to let a few more trickle in, and then we'll get started with our workshop for the day.
Good morning.
Okay, I think that's enough. We got a critical mass of people here, so we can go ahead and get started. So thanks, everybody, for joining us this morning for another Builder Forum series. Today's workshop is named Zero Carbon Step Code 201, a follow-up to our Zero Carbon Step Code 101 course we had here in April. We intend this workshop to go a little bit more into the nitty-gritties of Zero Carbon Step Code compliance, as well as talk to more of the technical aspects about being compliant with Zero Carbon Step Code, but generally with mechanical system design. And we also have a very special guest here today from BC Hydro to deliver a presentation around distribution capacity and be available to answer questions that we are receiving as municipalities across the province that we can't really speak to, but our representative from BC Hydro will be able to competently deliver that information to you and answer all of your burning questions here all in one day. This is a special day for us. We don't usually have this many intelligent people with us, these brilliant minds. So put on your thinking caps and let's get started with the day. This workshop is brought to you by Green Buildings, and that is Kira Lai, our technical assistant, Jean Surendran, our building energy specialist, and myself, Ken Ramu, manager of the Green Buildings Department. And we're supported by CSA, Canadian Association of Consulting Energy Advisors, Architectural Institute of BC, BC Housing, and Building Officials Association of BC, who all will deliver credits to all who stay for the entire workshop. I'd like to start our workshop with a land acknowledgement. I would like to acknowledge the traditional territories of the Coast Salish peoples, and in particular acknowledge our relationships with the Katsi, Kwantlen, Matskui, and Simiamu First Nations. So our menu for the day for our Zero Carbon Step Code 201 workshop, the Township of Langley is going to deliver a very brief introduction, a few notes, and one important compliance piece that you want to be ahead of to make sure your building permits get processed without any delays. And then we're going to introduce Bertine Stelzer from BC Hydro to talk about capacity and distribution. Then we'll move on to Todd Backus, representatives from Thermal Environmental Comfort Association, otherwise known as TECA, to talk about the CSA F280 design methodology. And then lastly, our meat of the day, our main course is Tom Giltenan of Bernhardt Construction to talk about Zero Carbon Step Code 201. Particularly this workshop is following up on our previous workshop, which was really compliance from a modeler's perspective of how we make Zero Carbon Step Code work for you. We wanted to bring a builder to the stage to talk about how two builders can make Zero Carbon Step Code work for them. Okay, a bit of a recap from our April workshop, Zero Carbon Step Code 101. We had Emma Conway from E3 Eco, a modeler, who delivered an excellent introduction to zero carbon step code. She talked about design for zero carbon step code, complementary, or how you can make it complementary with being compliant with the BC Energy Step Code. She discussed all the different interesting multiple paths to compliance. And importantly, she highlighted that compliance with zero carbon step code has no additional paperwork. It comes with BC Energy Step Code paperwork, which of course is required throughout the province at a minimum of step 3. And if you missed that workshop, please check us out at tol.ca. It's right there on the bottom of the screen, tol.ca/gblearn. tol.ca/gblearn, where you can see our link to access to our Green Buildings Learning Hub or Green Buildings On Demand Learning Hub, where we have all of our previous workshops recorded. And you can register, watch any of those videos on demand at any time from anywhere, and still be fully accredited for watching the video. So please, if you haven't taken a look at that April workshop, I suggest you do, and get your credits while watching. 2 reminders. As of April 1st this year, Township of Langley requires, for energy and emissions compliance, Step 4, the BC Energy Step Code, and EL2 of the Zero Carbon Step Code. And April 1st, 2025, we require Step 4 of the BC Energy Step Code and EL3 of the Zero Carbon Step Code, both for Part 9 Group C occupancies. And as a reminder for any of those in the group, Part 3 circles, we require Step Code for Group C at Step 3, and we have since 2022. Everything else that's not on this page here will follow the provincial minimums, which is around 20% better. We, after all of our workshops or interactions with industry, we ask everybody who attends to provide feedback on how are we doing? Are we getting it right? Are we going too slow for you? Are we going too fast? And everything in between. So we do issue surveys, and we appreciate your feedback. Your feedback really helps us know if we're getting it right, and as well, if we should continue putting resources to these types of events. So we appreciate your continued participation in our surveys, and we will issue a survey after, actually during this and after this workshop for you to fill out. I strongly encourage you to fill that out and give us your thoughts and let us know if we should continue providing these types of services. I just wanted to highlight some of the feedback we got from our last workshop. One of our questions we had asked was, have you had any experience with the Zero Carbon Step Code? This will give us a sense of where industry is at. And you can take a guess, maybe in your head or in the chat. By the way, we do have a chat function here, so maybe you can say hi and as well issue questions there. Or if you can, if you wish to take a guess at this question. So we surveyed and asked, have you had any experience with the Zero Carbon Step Code? And it was interesting to see how many had experience with the Zero Carbon Step Code. It's only been around, well, it's been around for about a year or so, I say. 23% of respondents had experience with EL1, and kind of filtering down all the way to EL4, 11% of folks had experience with EL4, which is a bit of a surprise, where we would see typically people having experience with Step 5 of the BC Energy Step Code at probably 1 or 2%. So that's really interesting data we got back. And how many people had not had experience or no experience with the Zero Carbon Step Code at all? Was 43%, which is an interesting number. So that tells us that there is a significant amount of people who do need some help, who could probably benefit from some tips and tricks, and particularly learning from very experienced consultants such as Tom, Todd, and support from Bertine can really help them make Zero Carbon Step Code and BC Energy Step Code work for their businesses. And lastly, we asked, have you even heard of it, Zero Carbon Step Code? And 9% had not heard of Zero Carbon Step Code before that workshop. So yeah, it looks like over 50% of folks could use some help. And as well, we always ask after all of our lectures, basically, had you learned something? And then the phrasing is, after this event, has your confidence in building the zero carbon step code and Part 9 buildings increased? We asked this for every single workshop, and it was around 84% had said it either increased greatly or increased a little bit. And I want to note that this is the highest kind of reporting that their understanding of the topic had increased. Typically, it's almost exactly always 80% after every workshop. So this tells us that matters around zero carbon step code, they want more, and there's more to learn out there for them. So that's why we're also conducting the zero carbon step code 201 workshop. I want to highlight a requirement here at the township, and as well, it's coded in the BC Building Code per that should say 9.3351 and 9.33.3.12, supporting zero carbon step code and step code and basically mechanical system design. We do require through BCBC heat loss, heat gain calculations to be conducted in accordance with CSA F280. If you're wondering, you're scratching your head, what is that? Don't worry, Todd is here specifically for the reason to teach you builders, designers, everybody across the spectrum about what that is and how to be in accordance with it. We do require it. It is on our website. It is on our checklist. Thereby, if you haven't not demonstrated you have completed your heat loss, heat gain calculations in accordance with CSA F280, you will not be able to proceed through the building permit process. And I'll highlight, if this is kind of what you're talking about, this is new to me. It has been a BCBC requirement since 2012, or BCBC 2012. Quick plug for our Green Buildings On Demand Learning Portal. Learn and earn. Learn all about step code compliance and everything that's going to help you continue to build homes and buildings and earn your credits. Check us out at tl.ca/gblearn. We have on-demand education videos, slides, and more. Maybe Kira, you could put the link in the chat for those who want to load it up pre-ready to take a look after the workshop for today. All of our courses are accredited. This is, I'm 99% sure, in the context of free education, it is the first in BC, and I would not be surprised it's the first in Canada. We're fully accredited by BC Housing, AIBC, BOA BC, Canadian Association of Consulting Energy Advisors for the majority of our courses. All of them are accredited by BC Housing to help you continue to operate and learn. Watch anytime, anywhere, get your credits. And importantly, it is free. Okay, that is our very quick, and I think I'm on time, introduction for today. We have a lot to go through. I'd like to introduce our first speaker of the day, and that's Bertine Stelzer. Bertine Stelzer comes to us from BC Hydro. We specifically wanted to reach out to Hydro, as noted, to get their explanation on what's going on here. It seems that we can answer the questions around design, BC municipal matters, all these kind of neat things, but around BC Hydro, we are simply uneducated in those matters, and sometimes I understand. Especially for builders or others on the call, it might seem like a bit of a black box of what's going on behind the scenes at BC Hydro, but it is not. Much or all of this is public information. It's just that we, as municipalities, are not competent in these matters. So we got BC Hydro themselves to agree, and they were happy to come and to deliver information, to answer a whole bunch of kind of burning questions that we seem to get repeated at our different interactions with industry. Bertine is very competent in these matters. He is the program manager for new construction with BC Hydro's market transformation team. Bertine was an important component of the step code deployment across the province, and she continues on to support markets, being ready for upcoming code changes, working with folks just like yourself, all of you on the phone, including people like us here at municipalities, supporting education, training, communications around zero carbon step code, code standards, and everything in between. So please join me in welcoming Bertine Stelzer, talk about BC Hydro distribution and capacity.
Thanks so much,
you,
Kevin. Thank you for the introduction. I'm just doing a double check on whether audio works fine. You can hear me great. Okay, wonderful. I'm going to bring up a presentation, so just bear with me for a second.
And maybe while Bertine's doing that, I forgot to highlight, so Bertine here is deliver information as well, answer questions. We have up to a certain amount of time that she'll be fully available to answer questions. So I strongly suggest enter your questions in the chat. Due to the kind of time allotment we have for Bertine, we're not taking questions live during her 15-minute presentation. So please plop your questions there in the chat. And then once Bertine is done with her presentation, I will facilitate those questions in the chat and as well take some questions live during that time. So for now, please enter your questions in the chat. She won't be taking them live.
All right. Thanks so much, Kevin, again. So yeah, the request is really for the chat because I have a ton of slides to go through. And if I get stopped, and I'm pretty sure I would get stopped, is just to be able to deliver you all the information that I was hoping to talk about today. So just a quick introduction again from me. I work with market transformation here in BC Hydro. I'm a program manager. All the information I'm going to present to you today comes from various departments across BC Hydro, so I'm barely able to touch on a bunch of things, and we'll give you the 360 overview on a bunch of big questions. I'm joining you today from our downtown office, which is located on the unceded and traditional territories of the Squamish, Tsleil-Waututh, and Musqueam people. And as BC Hydro, we're obviously operating a large infrastructure across the province. So we are touching on many Indigenous lands and are really appreciative and thankful for the ability to work with our Indigenous partners across the province. So in preparation for this webinar specifically, I connected with the Township of Langley to understand what are the top questions that they're getting. And this is really the summary of what I'm going to talk about today. Is I'm hoping to give you a quick overview on the big question: do we have enough power today? Like, what does our generation and distribution system look like today to accommodate zero carbon step code adoption as it happens as we speak? The second big question that Kevin shared with me was around where will our future power be coming from if we're going to electrify many of our systems, if we're going to electrify a lot of our passenger vehicle traffic, etc. So I'll touch really briefly on our integrated resource plan and also how our grid just works in general and where that interplay and integration of our grid capacity is going. And then lastly, there was a question around how do we respond to gentle densification needs? So given the policy context around gentle densification, Bill 44, like everything that's coming at local governments and as well as you as an industry has an impact on how we do our business on a day-to-day basis. So I'm hoping to touch on some high-level things around how we do our distribution design and connection services, what the cost questions are, which is a big question, of course, and then some of the work that we're involved in as a team and within market transformation with our partners, such as the CHBAs, et cetera, around design and technology solutions. So a lot to cover. Please bear with me. I'm trying to go as much into detail where I can reference questions that we have gotten from industry, and then really much invite everyone to type their questions in the chat. So first of all, power today. BC Hydro is the largest electricity provider in the province, as you're probably familiar with. We're a Crown corporation. We serve about 5 million customers across the province. This is what our system looks like. We have 30 hydro plants, about 125 independent power producing projects that vary from water, wind, and solar resources. Our network of transmission and distribution lines is around 80,000 kilometers. So I guess twice around the world, and we have over 300 substations across the province. A really important grounding piece for a lot of people is this information, which is that our end energy use is currently supplied by electricity by only approximately 19%. It's under 20. The province sometimes references 17, Florida sometimes references 16. It's in that ballpark between 16 and 19%. It varies. But the majority of our end energy use comes from fossil fuels. So if you think about your cars, your homes, industry, commercial endeavors, etc., 70% of that energy use comes from fossil fuels today. So when you hear that word energy transition and change in the utility world, it's really looking at that percentage and seeing how that changes over time. But this is the starting point where we're today. Now, if you focus in on that 19% electricity supply to end usage, this is how it looks like on the BC Hydro side. About a third of our electricity goes into large industrial applications. About a third goes into commercial and light industrial sectors, and then about a third is our residential sector, so the sector that most of you are working in. Now, if we scale that down even further, we collect data on a regular basis, and this is some data from our residential end-use survey from 2020. We have 2023 results. I just haven't had a chance to update this. It's not super significantly different, but it just shows you by region what the current electricity use for home space heating and water heating looks like. And this includes both multi-unit residential spaces as well as single family. So you can see here that the Vancouver Island is usually considered the already somewhat electrified space because space heating and water heating makes up over 60% in their residential space. Township of Langley would probably fall into the Lower Mainland category, where we see about 40% electricity used for space heating and about 21% for water heating. To end this, like, what does the situation look like today section of this presentation, is I wanted to put the slide on that talks about our peaks, because peaks come up a lot in terms of the big discussion, like, are we ready? Do we have enough electricity, et cetera, et cetera. So what I bulleted here is the 3 peaks that are the most recent peaks on our system. December 2023 was a record year in the month of December, with a cold spell that happened over, I believe, a week over Christmas, if I remember correctly. And at that time, we reached 10,977 megawatt of energy supply that we provided through our grid to residents or to our customers in general. And so that was a record peak at the time. On August 14th in 2023, we had a first kind of summer peak. Obviously, it's much lower than what our winter peaks still are. We are winter peaking utility. Locally, we see some summer peaks now happening. But August 14th was a bit of a special year. We had a warm spell there, and we reached 8,400 megawatts of supply. And the latest peak, which was the highest, again, record, was January 12, 2024. So just this year, where we, on one evening, I think it was a Friday, we reached 11,300 megawatts. What's interesting is while we are absolutely getting closer to our total generation capacity, which is just above 12,000 megawatts, at that moment in time in January, we were still delivering additional electricity to Alberta. And at no point in time for these peaks did we require any imports. So it's just something that is not maybe fully or is information that people might not look up. It's obviously fully available on our website to find this information. But it's just something we want to share with audiences, because while we're getting really close, we're still A, not at the peak, and B, the fact that we're drawing our electricity from hydroelectric power, it gives us a really solid foundation to still be resilient in those moments in time. And then the last piece of information here is that this is kind of how our system works on a very simplified graphic here. So we have transmission networks, we have substations, and then we have the distribution grid that gets electricity to specific places. So today, and I'm going to relate to that further in our future energy planning, the real gist of challenges that we see coming up for builders and for customers is not so much on the generation, it's on the way how we distribute our electricity to specific sites. So just want to put that attention there. Now, when it comes to planning for the future, there's one document that every utility has to produce as part of their business planning, and that's our integrated resource plan. So as a utility, we are asked by the Utilities Commission and by the province and everyone else to lay out what our plan is to generate electricity into the future. So this is our integrated resource plan that was approved by the BCUC in 2021. Which basically is the foundation for how we plan for our energy supply and generation over the next 20 years, 30 years. So this is really the grounding document here that helps us in planning. And we did a big review of our integrated resource plan last year. And that generated a bit of an update. And so this is really a summarizing slide here that I wanted to show because this kind of tells a bit of a story. So in the past 15, 20 years, we actually have had a really constant demand on our electricity grid, despite population growth, despite new economies coming in and buildings being built. It's only very recent that we've seen a bit of a different trajectory in how our electricity demand is going. And so the reason why there's been stability in our last 15 years is because, as I showed you earlier, our supply goes into industrial applications, into commercial and light industrial and residential. So where we may have seen a bit of a surge in residential uptake because we have more population, we have more buildings, etc. We have seen quite a bit of decline on the industrial side because, for example, forestry sectors that have closed business, mining sectors that have closed business in BC, which are big customers of ours. So that is one of the reasons why that curve actually stayed really stable, because wherever there was a decline, somewhere else came up. So it's kind of buckets going up and down as you move along. Now, since the pandemic and since we're coming out of the pandemic, there's a ton of changes, right? On the policy side, on population growth, on new industries coming into BC, and a lot of push for decarbonization. And that's decarbonization not just of the building sector and the transportation sector, but also a lot of decarbonization requests for the industry, which includes our partners on the fossil fuel side who are looking to decarbonize their grid. So thinking of LNG, hydrogen, etc. These are all industries that are looking to decarbonize, and they're looking to us as the electricity provider to do that. And I didn't say that specifically in this presentation. I hope that's clear. It's because we generate 98% of our electricity from clean resources. So we don't have that added challenge to decarbonize our grid per se. We only have to decarbonize that last 2% of our electricity generation. So here, what you see are the scenarios for an accelerated transition of our electricity demand. And so we're planning for multiple scenarios because we don't know how the market is going to develop over time. We can make assumptions, we can make short-term assumptions, and we can make long-term assumptions based on policies and regulations, based on where the market is going. And so we have to be able to be flexible and nimble to these different trajectories of our energy demand. And what we're projecting right now is that by the end of 2030, our electricity supply needs to grow by 15% because that's the demand that we're expecting in addition to what we're supplying today. So how do we close that gap of 15%? It's not a small gap. One of the actions is bringing on generation through Site C. And that's going to add about 8% to our current supply, equivalent to powering about 500,000 homes or about 1.7 million electric vehicles. Another big action that you've probably heard of is that we initiated a call for power earlier this year, our first call for power in 15 years. It's the largest we've ever had. And it's looking to supply an additional 3,000 gigawatt hours per year. And that would be an equivalent of 5% more. So we have 8% through Site C, about 5% through that call for power, which leaves a couple of percentages more to generate electricity. And we're hoping to achieve that by our 36 billion capital plan, which was also announced earlier this year. And so some of that 36 billion is going to go into infrastructure investment, obviously on the distribution side, and that's probably what most of you are really interested in learning about. But it also includes investments into our existing infrastructure, and where, for example, in Revelstoke, we could add another generation tube to an existing dam that again can generate more electricity. So it's a huge amount of money and a huge amount of spending that's going to go into our infrastructure moving forward, and that's going to make up for that 15%. Township of Langley specifically, so out of that $36 billion investment, there's about 725 million going into the Township of Langley area to provide funding for substation expansions, for new substations being built, and then major distribution investments into underground and overhead infrastructure in some of the high growth areas that were identified. So I'm not going to go too much into detail here. Now, also to say conservation is still important. Just as a reference, again, our energy efficiency programs have actually saved us and energy in the amounts of 5,400 gigawatt hours, which is almost the same size of Site C. So if you consider that over the last 15 years as well, which is part of the reason why we could keep that curve flat, and this is one of our major tools that we have in our toolbox as a utility to help navigate that growth in demand over time, and that plays into that 15% in our integrated resource plan as well. So it continues to be very important, and initiatives like the Energy Step Code will continue to be a very important tool in order to achieve that. I'm looking at time, and I know I'm already a little bit over, so I'm going to browse through this, so bear with me. Here's just a quick map of where you can find our different generation infrastructure. One piece of information that I think that's really important here is that we are not an isolated grid within BC. We are part of the Western integrated grid, and so a lot of our energy supply is also impacted by how we trade electricity. So our biggest trading partners are Alberta and south of the border, so Washington. And we get a lot of questions around, well, last year during drought season, we had to import quite a significant chunk of electricity from our southern neighbor over many, many years. So we're actually a net exporter of electricity because we usually have surpluses that we can sell to other jurisdictions, and they're really interested in our electricity because it's clean. And so then the next question is, well, are we getting dirty energy then from our southern neighbors or eastern neighbors when we import? And the answer is yes and no. Generally speaking, the power that we purchase needs to be cost effective, because otherwise we would have to increase our rates. So often what we get from our southern neighbors is surplus electricity that's being generated by renewable plants. So it's the solar energy, it's the wind energy that's being generated all the way down the Cascadian area. And we're often paid to get that, to take that electricity, because it has nowhere to go within the United States grid. So that's one piece. Also, as a utility, we are subscribed to clean energy requirements. So again, as a utility, we are bound to BCUC's and the province's Clean Energy Acts. And so we actually have to report on our emission factors. So it's not in our interest to buy dirty coal electricity that's in the south. We actually have to report on that. And so if you look, again, this is all public information that you can find on our website. to show what the emission factor is and how it nets out between our own supply versus what we import from our neighbors. So just a little fun fact about our grid. And again, this grid is actually helping us too. Like if ever we were in a situation that we would need more electricity, we could tap into that grid to help us out if we needed to. It has never happened. It's usually the other way around, that we're the ones providing more electricity. Okay, gentle densification. I'll try to do this in 2 minutes. Was the last piece. So here's just to summarize that some of the things that we're doing to help with customer connection improvements. So obviously, we are experiencing a record high in connection applications. We're also experiencing a record high in different connection applications because now single-family home builders are moving into that higher ampage size panel design piece, which drives them to a different connection process than they may have experienced in the past with a 200 amp panel. So that means that we needed to massively staff up our regional design offices, and that's what has happened over the last 12 months. With its pain points that come with staffing up, it's staff that needs to be trained, it's staff that needs to be specialized. So while we're amping up on the people capacity, we rely also on training and getting these folks into their jobs, but it's something we're actively working on. We started to heavily partner with municipalities in our high volume and high growth areas to improve permitting and approval processes. So for example, looking at questions like, do local governments really need to enforce that undergrounding requirement, which some of local governments have? Or can we work in partnership with local governments and let BC Hydro help to decide what's the most cost-effective and quickest way to get a project connected? So there's ability there to be flexible, and we've seen some really great innovative approaches to that process with some of our local government partners. Of course, we want to reduce timelines for connecting customers. So again, most of you are probably now in the complex design applications because you have a 400 amp plus panel. We're really looking at efficiencies on that end and trying to make sure that we can process these applications faster and more effectively as they come in. And then we also get a lot of questions on a 300 amp service because a lot of times builders find themselves in between the 200 amp versus 400 amp service requirement. And so we do have some pilots out with a 300 amp service connection. Our bottleneck at this time as a utility is that we need equipment for that, and we have a supply chain issue in getting actual equipment for this 300 amp service. But as soon as that's being resolved, we're looking to roll out that 300 amp service connection opportunity more broadly. Another piece I would just want to bring some attention to is the update of our extension fee policy. So again, because probably some of you are now pushed into a higher ampage service size, you may be also pushed into the hot seat in terms of paying for upgrading infrastructure on site, whether it's a pad-mounted transformer, whether it's distribution line upgrades, et cetera, et cetera. So currently, our extension fee policy is kind of penalizing the first person that issues that upgrade, and everyone else who's going to come consecutively is going to benefit from that first investment. It's not a fair process. It costs way too much money. There's a lot of charges being put on the customer as opposed to BC Hydro. This is all regulated by the BCUC, so we're submitting a application to the BC Utilities Commission actually in 2 days from now to update that distribution extension policy and look at standardized connection charges that are not going to penalize one builder or developer who is triggering that upgrade anymore. Okay, and then lastly, just to mention, there is obviously lots of solutions on the builder side themselves. We've been talking a lot about integrated design, mechanical system design. That's our speakers for today, who can dive deeper into these best practices. And hopefully they will touch on some of these opportunities that we have through our electrical code and through Technical Safety BC, where at least for the retrofit sector, there's opportunity to do historic load calculations that may help you to keep panel sizes low. and making use of these rules in the electrical code that allow to use load sharing devices when it comes to electric vehicle charging. So I'm going to leave it at that because I'm way over time, but happy to answer any questions at this time. Thank you.
Thanks, Bertine. That was a great presentation. So the floor is open. I don't see any questions in the chat. So, Ajin, is it they put their hand up, or how can people ask questions?
Yeah, so
Yeah,
there are two ways.
okay.
You can put in the chat, and or you can just raise your hands. We can unmute you.
Okay, raise your hand. It's at the top of your screen.
Yeah.
There's some icons there. So there's one hand looking like this. So click that, and Najeen will be able to unmute you. Or there's a question here by Nazmal. He asked, will we get the recorded video? Yep, we will record this. This workshop is recorded. It's going to be on our website at tworld.ca/gblearn, and it will be there for everybody to watch.
Yeah, so maybe
go ahead, Bertine.
Sorry, while we may give folks time to put some questions in. So this was a really quick, high-level presentation, and I'm actually on tour with the Canadian Home Builders Association of BC to dive into those exact same questions in a more lengthy format and with an opportunity to actually engage in a conversation on the spot, because these are in-person events. If you feel like you need to digest this first and kind of figure out your questions, I think there's openness here, to share these dates, or if you want to come out and actually talk to us in person, that might be a preferred way to get your questions out. So, and any questions are very welcome. We do this tour also alongside Fortis because we are quite interdependent in terms of how we're going to tackle that energy transition moving forward. And so it's a really helpful format for folks to get their questions out. I do see a question here, hoping to speak a bit more about load sharing, that last slide. I don't know how much I can actually competently talk about this. I'm hoping the speakers today will touch on this a bit more. But just on a high level, so the electrical code is what governs and basically tells you what the panel size is that you need to put into your homes. We got a lot of questions recently from builders in Whistler around, well, like zero carbon step code is going to drive our panel size into the absolute abyss. Like we're seeing 1,000 amp panels and 1,200 amp panels. I'm like, whoa. Where is this coming from, right? So one of the pieces of clarifications is always the zero carbon step code does not regulate any systems that are outside of your home systems. So if you're talking heated pools, heated driveways, outdoor space heating, et cetera, that is not regulated through the zero carbon step code. The zero carbon step code really only regulates your home energy systems for space heating and water heating. And if you choose, or your local government chooses to do the prescriptive path, then it may also affect your cooking. Everything that is kind of a lifestyle appliance is not falling under those regulatory frameworks. So you should not arrive at a 1,000 amp panel. That is probably not a beneficial way to go for your customers or for yourselves, because you're looking at massive infrastructure investments, and it's not a great thing for us as a utility because you're not using that electricity in an effective and efficient way. So we really have to look at the electrical code to kind of guide our calculations on that end. And so today, the electrical code only provides some flexibility around EV charging and load sharing opportunities through various different appliances. So whether that is replacing your EV load with a washer dryer load at certain days through a switching device, or these types of technologies, that could be an option to look into to neglect that EV charging load on your panel. But again, I'm not the expert on this, so I will let the experts talk to that.
Thanks, Bertine. Thanks for that. And we do have a hand up, and maybe
Yeah.
for the sake of time, we'll take this question, this live question by Jody, and then we'll pass it on to our other two speakers of the day. So Jody, go ahead, ask your question. You're unmuted.
Okay, I just wanted to let you know that the chat function is not working.
Oh. Thanks for letting us know that, Jody. Okay, so we.
Yeah, I'll look into it.
That's a bit of a curveball for us, Jody. Yeah. Thanks for letting us know.
Yeah,
we do
no
see
worries.
Some notes here by Nicholas or some other folks here. So thanks for letting us know. So maybe with that, we'll if anybody else has a live question they wish to ask, please raise your hand now. We'll take. Oh, well, there we go. Okay, so we got some notes in here. Oh, okay. So we'll take this last question and then we'll move on. Harbir asks, with duplex to fourplex zoning coming in, there's no space there's no space on lots to put a pad mounted transformer and parking for 4 people. Is there a way to keep the 400 amps overhead service?
Awesome. Yeah, that's a great question. So great question. I think that depends on your local government's regulations. So I can speak here to an example from the city of Vancouver where they're allowing gentle densification now to happen. They're requesting a pad mounted transformer space on the lot. So you have to have that on your designs. But they're not enforcing parking stalls anymore. So it's up to the developer whether they want to put parking in or not. So I think that's creating the space that you're asking for in terms of, where to put that infrastructure. Now, that said, BC Hydro may be able to accommodate a 400 amp overhead service if the infrastructure is there to make that happen. There's overhead transformers that we can tap into. Et cetera, et cetera. So at the end of the day, it comes down to what the local government is requiring in terms of their design, spatial design requirements, and that's what's being submitted to us then to figure out what the best way is to connect that project. So maybe more of a question to the township than to us.
Thanks for the question, and thanks, Bertine, for that answer. I do see some other questions here and even a follow-up to that question back to the township. But particularly for the sake of timing, I think we'll kind of cut this section off and move forward. I do see some questions there, and that's fine. And for the rest of the gang on the call, if you have questions, put them in the chat. We will take all of those questions and answer them after the lecture. We will then send a follow-up, as we do for all of our workshops, in a Word document, and you will have access to all of your answers. So go ahead, and I see a question by Jazz and others. Go ahead and put them there. Bertine and us will answer those after and send a document out. So if you still have a question, please put it there. We will answer them. But with that, I'm going to pass that to Ajeen. Well, let's thank Bertine for joining us today. That was awesome. A lot of great information, and I think there's a huge demand for this information from Hydro. So thank you, Bertine. Again, put your questions there in the chat. We'll get to them over the next week or so, and you'll get an email from us with all of your burning questions answered. And with that, I'll pass it off to Ajeen to introduce our next speaker for the day and to facilitate the rest of the workshop. Thanks, everybody, and thanks, Bertine.
Yeah. Thank you, Kevin. Thank you, Bertine, and hope you both have a wonderful day. So, do you see my screen? Okay, yes. So we have our next speaker, Todd Backus. He's the program manager of developments for Thermal Environmental Comfort Association, or TECA as known to the industry. So he's got 20 plus years of experience in HVAC industry. He's got Red Seal ticket as a sheet metal worker, and he's also experienced in HVAC design. He is an owner operator of Backus Mechanicals and specializes in installation and design of custom homes. So I'm passing it on to Todd. He's going to be talking more about the technical side of like the design side of HVAC.
Thank you. I will just share my screen here. Perfect. Is that coming through?
Yes.
Excellent. Okay, welcome to my presentation on CSA F280 HVAC requirements for Part 9 buildings. I would like to preface this with, this is a very big topic, and we are just going to be doing a surface level examination of this. So I will do a little introduction, talk about the CSA F280 standard, some of the certified calculators, what are the code requirements, what you can expect from the heat loss, heat gain inputs and the reports, some common errors and omissions, and the 26-degree refuge room. I will go through an example of that at the end. And yeah, I don't think we're going to have a lot of time for Q&A, so please put those in the chat and I will answer them as best I can. So I was a sheet metal contractor for a number of years. I went back to school, got a mechanical engineering degree. I worked as a consultant, mechanical engineering consultant for 4 years, and now I'm with TECA as the manager of program development. So a little bit about TECA. We're a nonprofit trade organization, and really our mission is to further education in the HVAC industry. So today we're going to talk about CSA F280 12, our 2021, which is the full title of the current standard. And it is called Determining the Required Capacity of Residential Space Heating and Cooling Appliances. So what's covered in this standard is the calculation method for heat loss and heat gain with the intent of selecting equipment. It also provides methods for verifying the calculators, and it applies to Part 9 buildings. However, it does not comment on distribution systems or installation practices. I'm not going to go really far into the math behind the calculators because it's just much too much to cover in such a short time, but I do want to highlight a couple things about some of the calculations. So here we're looking at the heat loss of an above grade wall assembly. And this kind of calculation shows up a lot in the CSA F280 standard, where you'll have the area divided by the R value times the delta T. And that delta T is the difference between your indoor set point temperature, so the temperature that you want inside your home, minus the outdoor design temperature. And you see this calculation come up many, many times in the back end of these calculators. You will also see it's quite common to replace the R value with U, and that way it just keeps it straight multiplication, but just note that the U value is just 1 over R, so it's essentially the same thing. Now, when you get into fenestrations, so windows and skylights, there is still this area times delta T over R value calculation, but there's also this solar factor. So again, I'm not going to go into huge detail here, but this is the reason that orientation and building location is actually important to the calculation, because the calculator considers how the sun is hitting these fenestrations and generating this solar radiation within the building. So one of the limitations of CSA F280 that's actually very important to understand is that this is a peak load calculator. So the output is going to give you either BTUs per hour or watts, depending on if you're imperial or metric, and it's energy over time. So what this cannot do is simulate the buildup of heat in a dwelling over time. And that is a limitation. So this is a peak load calculator. We look at the absolute worst case scenario, and then based off that, we say, well, if we can meet the peak load, partial loads will be fine. And this is actually a little model that I made up. This shows heat propagation through a plate. So you see that it's like hot in the middle and then cooling as it goes to the outside. CSA F280 cannot do this kind of calculation. It can only look at an instantaneous snapshot in time and give you BTUs per hour in that moment. So as with any mathematical model, the information that you input into it is critical. We say in the industry, garbage in, garbage out. And if you model incorrectly, you might end up with a very convincing looking report, but you are going to have the wrong answer. So you have to be very diligent with how you enter the data and the accuracy of that data. So this makes it very difficult to determine the accuracy of the 26-degree refuge room calculation. I will cover an example at the end. So CSA F280 outlines how the information is supposed to be reported from these calculations. Some of the critical information is client and project number, the building location, what assumptions you've made during your calculations, what are the design temperatures used, what building envelope properties you have, as well as the contact information of the designer. And this is actually within CSA, this table that outlines, you know, what your obligations are as far as providing information in the report. There are a number of CSA F280 compliant calculators. So this is from HVAC DC's website. The link is right here. And HVAC DC is responsible for the third-party certification of these calculators. I believe they have to be within 1% of the base model. So you should get the same result regardless of which software you use, assuming that you have entered the same information in essentially the same way. So this one is TECA's, and that's the one that I'm going to be covering today in detail. Another one to be aware of is Volta Snap. It's very popular, especially among EAs, but be mindful that Volta Snap is really for the whole house. They do what's called a block load, where they will examine the entire dwelling. They will not look at a room by room calculation. Now, as a contractor and as a designer, I feel it is your responsibility to provide a room by room calculation in order to understand how this system should be divided. Because if you do a block load, you'll know roughly the size of the equipment that you need, but how much heating do you need in the living room? How much do you need in the primary bedroom? You will be essentially guessing if you have not completed a room by room calculation. So as a contractor, I feel it is your obligation to provide this, even if the EA has provided a block load. So moving on to the code requirements. Heating and cooling equipment is to be sized using the CSA F280 standard. The design temperature are prescriptive and outlined in the code. And then in the BCBC only, there is this refuge room, the ability to maintain 26 degrees C. I believe it's my understanding that this will, in the next cycle, apply to the National Building Code as well, but currently it's only in the BCBC. So this is the actual sentence from the code under 9.33.5.1. The required capacity of heating and cooling appliances located in a dwelling unit and serving only that dwelling unit shall be determined in accordance with CSA F280, except that the design temperature shall conform to section 9.33.3. So this was added in the last code cycle, and cooling appliances. Previously, this line only mentioned heating capacity, but now we're asking for heating and cooling appliances. So looking at the next line here, 933.3.1, the indoor design temperatures. So you have to, at the outside winter design temperature, required heating facilities shall be capable of maintaining an indoor air temperature of not less than 22 degrees C in all living spaces, 18 degrees C in unfinished basements and ancillary spaces, and 15 degrees C in heated crawl spaces. Now, this is the contentious item. So the following sentence is, at the outside summer design temperature, required cooling facilities shall be capable of maintaining an indoor air temperature of not more than 26 degrees C in at least one living space in each dwelling unit. Again, mindful this is only in the BCBC right now, but they are saying explicitly required cooling to maintain 26 degrees C in at least one living space in each dwelling unit. So the BSSB has released an information bulletin to try to answer some of these questions. I highly recommend that you look into it. It's called Protection from Overheating in Dwelling Units. It's only 5 pages long, and it covers some of the critical items like some passive cooling strategies, the energy modeling requirements, specifically to use CSA F280, not HOT 2000. And then also it mentions that the BCBC allows for a passive cooling strategy, and it refers to sentence 2.2.2.1, sentence 1 of Division C. Now, what does that say? It says, sufficient information shall be provided to show that the proposed work will conform with this code and whether or not it may affect adjacent properties. So clearly, we're not going to run into an issue with adjacent properties, but this comment about sufficient information shall be provided to show that it will conform with the code is ambiguous. So my interpretation of that is you need an engineer to sign off on a passive cooling strategy in order to take this alternate path of code compliance. But it is not crystal clear. This is a very ambiguous statement. So I would caution you, if you are looking into trying to make a passive solution work for the cooling requirement, you better be careful with that, because you might come into problems proving that it will actually work. So the outdoor design temperatures, those come from the BCBC. If you go into the appendix in table C, basically what we're looking at here is the outside winter design temperature shall be determined from appendix C, and they're the listed January 2.5% values. The outside summer design temperatures are the July 2.5 dry bulb values. So if you look, I have this blown up a little bit. So this is our winter temperature, and let's say we're in Abbotsford, so you're looking at -8. Our summer temperature, which is the dry bulb, coming over to Abbotsford, we're at 29 degrees C. Now, one thing that catches people off guard is there are a bunch of HVAC requirements in section 9.36. So 9.36.3.6 temperature controls, where heating and cooling systems are controlled by separate thermostatic controls, means shall be provided to prevent these controls from simultaneously calling for heating and cooling. So we might see this in a situation where you have a hydronic system. So let's say you have radiant floor heating and you've installed a ductless mini split system. Well, there are certain situations where your hydronic heating might be calling for heat at the same time that your ductless mini split system is calling for cooling. So you are actually supposed to have some means of preventing that from happening. And I have seen it happen in real life. So I would advise you to consider that when you're designing systems that could potentially be wrestling with each other, heating and cooling simultaneously. The other line here is heat pumps equipped with supplementary heaters shall incorporate controls to prevent supplementary heater operation when the heating load can be met by the heat pump alone, except during defrost cycles. So this I read as an argument against using the economic balance point, where you are setting up the system to switch to gas, say, if you have a furnace as a backup, in order to get cheaper energy. The code actually says you should really be using the heat pump 100% of its time. So the balance point should be set based on its efficiency rather than an economic set point, with the exception of the defrost cycle, which is logical. So looking at the heat loss and heat gain inputs and results, I'm going to walk you through the TECA heat loss heat gain calculator. There are other certified calculators, as I showed previously, so that information might be presented a little bit different, but what is required is outlined in CSA, so the outputs should essentially be the same, even if they're just formatted a little bit different. So some of the things to consider: the building location. So the latitude, as we mentioned previously, has big solar impacts. The orientation of the building, that is critical. Again, because of the solar impacts, you know, your north side of the building is going to see a whole lot less heat loss and heat gain at peak conditions than your south side or your east and west sides. Outdoor design temperatures, so those are pulled from the code. Building design parameters, so what are the assemblies of, you know, what makes up this building? There is a line to provide air tightness, the ventilation system, the mechanical system, and then the indoor set point temperatures, which are, again, prescriptive. So TECA's calculator looks something like this. This is the first tab. I'm not going to go into huge detail because we just don't really have time for it. But essentially, you enter, you know, your personal information, the project information, details about the house, details about the ventilation system, and that gets translated into this report. So again, this is TECA's report. Other reports should look similar, but not quite the same. So here we have calculations performed by, all the contact information of the designer, the project information itself, where, you know, where this model is located, the weather data, so the city, the ventilation system, quite important. So here I'm showing an HRV with 60 CFM of continuous ventilation, the heating system. So this example is radiant heating. One of the things that you'll find is there are a lot of questions about, is this value assumed? So here it's referring to the front of the house, which is facing southwest. And no, this value is not assumed. This house is going to stay southwest. But if for whatever reason the house gets rotated, this needs to be corrected because your calculations will be way off if you have the wrong orientation of the house. Here we have the air tightness and infiltration. There are a couple different ways you can enter this information, but it is very flexible. You know, if you have like a blower door test, you can take those results and directly input those. Again, is this value assumed? Yes or no? And then coming down to here, we have our indoor design temperatures, our outdoor design temperatures, and our occupancy of the building. If you have any notes, these will show up there. Now, moving on to the building assemblies. So there are a lot of different options for how you input this. This is this is the one I generally use. So when you're making your walls, windows, skylights, doors, and foundation assemblies, you have to go through and enter this information. Again, I'm not going to go into huge detail here just because of time, but what that report will spit out is this summary of your building envelope elements. So looking at the walls here, I've blown that up over here, and you can see there's each layer of this wall assembly gets put together and then summed up as a single R value. So this is always something that you want to take a look at. Look for that R value and just make sure that it's logical. Now, TECA's calculator does room by room analysis. This is critical to sizing an HVAC distribution system. Personally, I would never accept a system that was designed off the block load. The block load is fine for high level. So if you're quoting a job, if you're talking about like the overall performance of the building, that is fine. But when it comes to actually sizing your ducts or your radiant loops, you really got to know what each room uses. You can modify in our software the temperature in each room. There are a couple other things that you need to be mindful of. Is there continuous ventilation in this room? Are there occupants? Are there very high electrical loads? So all these things you end up just entering into the calculator and then they show up on the reports side. So this is a breakdown of the components. So here we have the heat loss component breakdown in BTUs per hour. So this is how you size your heating system. below we have the heat gain component breakdown. This is how you size the cooling system. So I have it broken down into room by room, right? So if we look at bedroom number 1, it'll tell you a value for the walls, for the floor, for the windows and skylights, the foundation, leakage, ventilation, and then it sums it up on the right. So you can look at what the performance of your building looks like from here. So typically you'll find that the windows are the highest on the heat loss. Often the walls are the next highest, and then you come into the foundation, leakage, and ventilation, and it all sums up over here. But this is an excellent way to kind of check your numbers too, because if you see one of these numbers that's just sky high, that's a good indicator that maybe you've hit an extra 0 when you were calculating the area of, say, a wall. Now coming down here at the heat gain component breakdown, same thing. So we have it broken down room by room, all the wall, ceiling, and whatnot. So again, windows, on the heat gain side, windows are even more dramatic because you have that solar gains. And actually in this example, the walls are not bad at all. The next highest is actually the internal loads. So the way the CSA F280 calculator works is it calculates the sensible cooling required, and then it times it by 1.3 to simulate the latent load. It's a shortcut, but it allows a very complicated calculation to be kind of sidestepped. So here we have our total heat gain load. Now be aware that CSA allows the minimum capacity for cooling to be 80% of the total load. So that's what this box is. There's your minimum. There is your actual cooling requirements. And then we also provide a heat loss and heat gain summary. So this is good for just checking some of the kind of fundamental information. So you've got your rooms, which floor it's on, what the area of each floor space is, and then your heat loss and your heat gain. These are the same as from the previous page, but it just breaks it down in a slightly different way. This is really good for checking just to make sure that the area of the dwelling matches what's on the plans. If you've missed a room, that's a good spot to find it. The other thing here is the results page on our calculator is set up to create it automatically. So there's very little burden on the designer once they've input the information to provide these results. You just go over to this tab and you hit print, and you can PDF it in a matter of seconds. So as a building official, if you're asking for this, like, you're not putting a huge burden onto the contractor to provide this if they have in fact done this calculation. So I highly recommend that to meet this CSA F280 heat loss, heat gain calculation requirement, you get a report that looks like this. I'm just going to touch on balance points for a moment. So this does not get generated by the heat loss, heat gain calculator, but I use that calculator to generate this line here. So this line is the heat loss load of a dwelling. So what we can see is we have our outdoor air temperature on the x-axis and our heating capacity in BTUs per hour on the y-axis. So as the outdoor air temperature falls, the load on the building goes up. And that's because the delta T in those equations I showed at the start, that's getting bigger and bigger, which means this line is getting bigger and bigger. Now, when you look at the performance of, say, heat pump 1 here, you can see its performance decreases as the outdoor air temperature decreases. This is normal when you're talking about heating. Heat pumps, their performance falls off as you get to the extreme temperatures. And where these lines cross, that's called the balance point. So if this heat pump 1 is running full speed at the balance point, so this is the last temperature, so that's, say, 25 degrees Fahrenheit. That's the last temperature that this heat pump can maintain the building loss load at. If the outdoor temperature starts to drop below that, you see this gap opening up, and that's the difference between the heat this heat pump can produce and the heat you need in this building. So if it's a short period of time, you might not notice that you get into this region, but over an extended period of time, what's going to happen is your indoor temperature is going to start to fall because you're not going to be able to maintain that capacity for that period of time. So from a code compliance perspective, this green line is the 2.5% outdoor design temperature. This is the code minimum that your heating system has to hit. So heat pump 2 actually meets that. Heat pump 3 exceeds it. You could use heat pump 1, but you would need some other form of heating to make up the difference here. One thing to keep in mind here, the 2.5 design outdoor design temperature, so that is accurate, or that is the lowest temperature that you're going to see 97.5% of the year. So there are still 2.5% of the time you are actually going to be on this region. And that's why personally I use the 1% outdoor design temperature, but the code minimum is 2.5%. And that's kind of what I was trying to highlight with this bin. You know, even though you might be, you know, serving this by code, there are going to be some hours that are actually below the code requirements. So you have to ask yourself as a designer, like, what is my client's tolerance for having that indoor set point temperature drop? You know, I work a lot in really high-end residential. And so for me, the answer is they do not have a lot of tolerance for not being able to meet like even the most extreme temperatures, which is why I tend to design further away from this code minimum. Right, so I recognize that a lot of people are not going to be completing these calculations themselves. I think we're going to find that a relatively few number of people are going to be responsible for the majority of these calculations. So I'm just going to comment a little bit on some of the things that you should look for in order to determine, like, is this accurately completed? So the outdoor design temperature and the indoor set point temperature, those are critical because that factors into your delta T that we've discussed a few times here. And that will impact like every single calculation in the program. So if those are wrong, you end up being way off. Look at the building construction and the assembly areas. This is harder to look at. That's buried within the model, but you can look at like the floor plan areas and just see, like, does that make sense with the perimeters of the walls? The orientation, as I mentioned, is really critical. The building latitude, so make sure the location is correct. The ventilation system, air tightness, and the correct mechanical system and controls are selected. So looking at the building assembly, I've seen a lot of errors here. So just give it a double check, make sure that it actually meets your code requirements, that it matches your architectural plans, and that it's not modified during construction, because you don't want to do your model based on, you know, a home that's very well insulated only to have those R values reduced, because then your system's going to be undersized. The other thing to be mindful of is units. I've seen the RSI values used instead of R values, or USI. So just be very careful that the units are correct, and they should be printed in these write-ups here as well. So it should be noted on the heat loss heat gain report directly. Fenestration errors. So because the windows and skylights are the highest loads, you really want to check those and make sure that the assembly's correct and that you haven't missed any of them, because missing a skylight is going to have a noticeable impact. That's going to be a pretty major error. So solar heat gains, when you're talking about heat gain, so cooling requirements, the orientation is important. Heat loss, it is not important for the orientation. So this is just an example of a 20-foot by 20-foot building with one door and one window per side. And you can see on the heat gain side, The windows change depending on the orientation, but the heat loss doesn't change. Overhangs, you can provide overhangs. You do not have to. The standard says specifically you do not have to include overhangs, but what it does is it helps provide shading, so it decreases your cooling requirements. So it's up to you. If you omit them, your calculation will be more conservative. CSA does allow for blinds and shadings. However, I do not recommend ever including them in your calculations because it relies on user input. So as I mentioned, I work in kind of higher end construction a lot of the time, and my customer is going to have a fit if I tell them, oh, the reason your house isn't staying cool is because you have to close all your blinds. Like, the first thing people do on a nice day is throw open the blinds. So I highly recommend not to include blinds or shadings in your calculation. Ventilation errors. The most common one is people will include all of the ventilation fans in the dwelling. That is not required. Only the principal ventilation system has to be included. So whatever fan is running continuously, that essentially is the number that should be input into the calculation. You should also make sure that you have an HRV or a bath fan noted correctly, because an HRV is more energy efficient than a bath fan. So getting on to the refuge room example, required cooling, we have to hit 26 degrees C in at least one living space in each dwelling unit. So this is something that a lot of people are going to run into. They're going to have a designer submit a heat loss, heat gain calculation for the whole house. And they're going to say, okay, I'm only going to cool bedroom number 2. Here is my heat gain summary, and I need 4,669 BTUs for this room. So here we go, bedroom 2, there's that number. Is this the correct number? No. That would be the correct number if you were cooling the entire house. But since we are only cooling, the proposed plan is to only cool bedroom 2, this actually is an inaccurate model. So why is that? In this example, the heat gain calculation was performed on the entire dwelling, not just bedroom 2. So they've modeled that there's cooling coming in here, there's cooling coming in here, in the floor below, in the entire dwelling, and then they're just cherry picking this one number for this bedroom. So they're ignoring all of the heat transfer through these interior walls and through the floors. Now, this gets a little bit confusing and difficult to deal with, because there is no clear standard for how you are specifically supposed to model this. All the code says is that you have to maintain 26 degrees C in one space. So be aware, this is my approach to meeting this requirement, but this is absolutely justified to say that modeling the whole house and then cherry picking one room is not a reasonable approach. So you've got to look at things like, have the occupants been included in here? Have the electrical considerations been taken into account? So to find the correct number, again, this is how I would do it. This is not laid out in any kind of standard or in the code specifically, but I would treat this one room as its own dwelling. So I would treat all of these interior walls as exterior walls, so the same R value as what's wrapped around here, and consider this temperature to be the outdoor air temperature. It is a very conservative estimate, but the energy transfer through the walls is actually not that big a deal, because as we recall, the biggest loads do tend to come from like the windows. So we're not adding any windows over here. This doesn't have as dramatic an effect as it might initially seem. The other thing is, if this is a refuge room, I would assume that all of the occupants will be gathered here, and they're going to be on their computers and their phones and doing, whatever form of entertainment. There's going to be an electrical load. So CSA does specify that a minimum 800 watts has to be assumed for an electrical load in one of the rooms. It's more than that if the square footage is high, but for the sake of argument here, we're talking a minimum of 2,730 BTUs, and one occupant is 300 BTUs roughly. So no matter what, you're going to end up with 3,000 BTUs of load in this refuge room if you model it the way I'm suggesting. Now, one thing that balances out some of this, like adding the wall business, is that your indoor temperature set point only has to be 26. CSA and like typical calculations use 24. So you actually get a little bit of energy back with this reduction of set point temperature. So here's how I've modeled just this room. And you can see like this wall value has actually significantly decreased from the whole house. The reason for that is, 49 versus 63. The reason for that is because we changed the set point temperature. So you'll find that propagate through the ceiling, the windows. The windows have come down, right? Leakage, ventilation, but here is the point. These internal loads, which are the electrical and the occupant load, I've made sure show up in this bedroom. Whereas in this inaccurate model, it's been shifted into the kitchen and living room, which is very normal for a whole house. But to then ignore that number and just select this, that's basically the difference, is that you've shifted this internal load into a room that you are ignoring. So I would highly recommend that you don't do that when modeling this accurately. And again, be aware, you only have to meet 80% of the heat gain for minimum sizing according to CSA. I would personally still use the total number, but basically what I'm getting at here is this is a 3/4 ton system. This is a 1/2 ton system. So this does actually matter when it comes to properly sizing this system. That is about all I have time for. So we do have a lot of training provided at TECA, including a much longer course. It's 2 and a bit days for this heat loss, heat gain calculation course, and we run through a full example in quite a bit of detail. So that concludes my presentation. If you do want to reach out to me personally, feel free. You can give me a call or send me an email. I love questions, so if you have any questions, please fire away.
Hi, Todd. Thank you for your presentation. So we have a lot of questions on the chat. So I was thinking, like, in the interest of time, you could if you could respond to those questions in the chat, because we're kind of getting too close to the time limit. So
I know I don't want to eat all Tom's time. I will absolutely respond to them directly in the chat.
Yeah, that would be great.
Perfect. Thank you.
Yeah, thanks a lot. So yeah, if you have any questions to Todd, you can reach out to him. If you have any questions to Green Buildings, you can send it to us. Now, with that, we'll move to the next presenter. So it's Tom Giltenan. He's an energy advisor for Bernhardt Contracting and is based in Roseland. And he is a journeyman electrician. Oh, so I thought I was sharing my screen. I'm sorry. Yeah. Okay, I hope you see my screen. Yep. Okay, so he's a journeyman electrician, and he has almost 30+ years experience as a carpenter. He's a lots of qualifications, education. I mean, he's an energy advisor, MERB-Q certified, and CSA F280 certified. He's part of Nelson Embodied Carbon Advisory Group, and also Roseland Energy Task Force. So I'm leaving this to Tom, and he's got a lot to talk about his experience with zero carbon step code. Tom, the floor is yours.
All right, thanks. I'll share my screen. And all right, can everybody see my page there? Heating and cooling. Perfect. Okay, so this is a presentation on heating and cooling, specifically working with the energy and carbon step codes. So I work for Bernhardt Contracting, as G said. I am an energy advisor. I have been working in the construction industry for as long as I can remember. My dad handing me a hammer when I was 6. I've been a carpenter for almost my entire life. I was an insulator up north for a while. I owned a landscaping business when I was in engineering. I did engineering for a few years, thought I would leave that and become a high school teacher for history and geography. That lasted for a year or two, and then I decided I'd get back into the construction industry. I became an energy advisor. I'm also an electrician. Oh, geez, there's so many, I can hardly remember. Anyway, but now I'm back teaching, and probably making my mom the most happy just to actually using my degree. So anyway, so moving on, today we're just going to do a very high level review of the zero carbon step code and stuff, since this is basically a second presentation on that for you. Some of the homes today and some of the numbers that have come up, we basically took all of the homes from the CHB ABC database over the last 4 years, about 5,000 homes, just under, and we put them into our heat program that we create, heat.ca. All EAs are able to use this if you sign up. And basically we can then extract a whole whack of information with very little effort, much less effort than running individual models. The houses in this that we looked at were basically mostly in the Greater Vancouver and Island area, and then a little bit in the Thompson and Okanagan. Apologies if I'm going very quick, but I am very mindful of the time we have. So the energy step code deals with energy loads, but not emissions. So what do we do with that? We also need to deal with greenhouse gas limits. So to do that, we have brought in what I have in quotes as the zero carbon step code, and you'll see why it's in quotes here shortly. This is not a timeline. This is an emissions goals comparison, essentially. So the 2018 code minimums versus the Clean BC emissions targets for new buildings, very drastically different opposing ends. Step 4, net zero, runs right around in the middle. Then we get to step 5, a little bit better than step 4, net zero, but we're still not meeting the target. And in order to get to those targets, we are now introducing our carbon step code and the EL4, which is zero, quote unquote, carbon. We also have a 2030, in 2030, we have 100% efficiency rule coming into play. I will bring that up later for space heating and water heating. This will become very important when selecting your systems. So of those projects that we looked at, half of them were permitted in the step 1 and 2, and that was basically before the code requirements obviously came in. Since then, half of the homes that have been permitted have been, or sorry, a quarter of the homes that have been permitted in the BC province have reached step 4 or 5. And this is relatively new, so we can see that the effort isn't drastic. The correlation that goes with the new EL3 and EL4 requirements with step 4 and 5 is pretty relevant, or sorry, you can see it pretty easily here. You can see EL2 is a majority of the ELs, apart from EL1, that's typically because that's just measure only, and that information came before we were required to label it. The thing here that I like to show is EL3 and why it's so much smaller. Basically, what happens with this code is that if you are working towards electrifying or the EL program, once you get into EL3, you almost automatically come into EL4. The only time you run into EL3 typically is if you're designing an EL2 house and it just so happens to reach EL3, or if you're designing an EL4 house and you need some work to do. So what does this look like in our area? With local policies and stuff. So in Surrey, please update your website. It is out of date. Richmond, you're step 5, step 3 with an EL4 requirement. North Van is step 5 or step 4 with EL3 requirement, step back program. New Westminster, also step back program, step 5 or step 3 with an EL4. Burnaby, step 3 with EL4 as of January 1st this coming year. And where we are in Langley, now it's step 4 with EL2, excuse me. And in 2025, we're moving to step 4 with EL3. Commissioning conditions may be required as well. Some definitions to go through, and this is probably be helpful after Todd's presentation because I knew some of them came up. First and foremost, zero carbon step 4 code in this presentation and for your mind should be not referred to as zero. This is false advertising. It in no way means it has to be zero. Instead, we will be looking at EL1, which is measure only, EL2, 3, and 4. A hybrid system combines 2 or more space heating technologies. So this could be like a heat pump with a furnace. A dual system is different. A dual fuel heating system is different in that it is using 2 different fuels. So electricity, natural gas. A principal heating system. This is your main heating system that does the majority of your heating. Supplementary system will come on when the primary system is not meeting the full threshold. This is not a backup system. If your first system goes down, the system does not come on to replace it, which then brings us to a backup system. This refers to additional systems. Now, best backup system we could probably provide would be a battery or generator. This would, in turn, if the power goes out, you could still then run your house and your heating systems and equipment. Moving on. So what is counted and what is not counted in the zero, quote unquote, carbon step code? So principal heating systems, they are counted. Your greenhouse gas emissions are counted towards that. Supplementary heating systems are sort of. We'll get into this a little later, but they can often not be counted or they can be counted a little bit. You'll see in a little bit here. Hot water tank is definitely counted. Your hot water heating. This could be a tank, a boiler, whatever system you have. Backup systems are not counted towards this. So generators, fireplaces, wood fireplaces, these are not counted towards the carbon step code at all. Now, cooking and equipment and appliances are not counted, but they are counted in the prescriptive version, and which you probably covered last presentation, and it is a much more restrictive pathway for that very reason. So what EL level is this house? So if we were looking at this house as an example, anywhere in the world particularly, but as an example, the principal heating system is a heat pump. The supplementary heating system is a gas furnace. We have a hot water electric tank. We have a diesel generator for a backup system. For equipment and appliances, we have gas cooking and gas laundry. And then we have other systems. So we have a heated driveway here, gas heated driveway. We have a gas barbecue. We have a gas heated pool. And we have a gas patio heater. And last but not least, we also have a gas heated garage. Now, all this gas does not mean it is not an efficient house in terms of the zero carbon step code, because that zero is in quotations. This house is actually an EL4, quote unquote, zero. And that is because we see here, the heat pump system is electric. This is not considered in the calculations because we have a primary heating system as electric. We have an electric hot water tank, and that satisfies our goals. So moving on, when a heat pump, heat pump performance, and why is this important? I know Todd went through this, but this comes into big play with how we use our heat pumps, specifically in the lower temperature areas. So an average Penticton house, the coldest day of the year, so that's that 2.5% Appendix C rating that Todd was going through, they are about minus 25. The heating needs of the house are this blue line here. So when do we need auxiliary? So this basically what this is showing is this heat pump will handle the heating loads, the heating requirements of this house all the way up to the temperatures, or sorry, the efficiency of the heat pump. And where those two lines cross is where you would need supplementing heating. So this is when you would need supplementary heating. So this could be a gas furnace, electric furnace, radiant heat, all of the above. Okay, so that is when you will need supplemental heat. Now, if we look at this same project, sorry. This is only for 1 to 2 weeks of the year at the very coldest point. So right here, for 1 week of the year, you would need supplemental heat about that much. For another week or two, you'd need quite a bit less, about a third less, according to this graph. This basically shows that for a very small time of the year, you will need supplemental heating, even in a colder area of Penticton. And so when we think about our costs of hookups, our gas hookups, specifically the monthly cost of having the gas hookup, you have to kind of ask yourself, is the natural gas worth having for that 1 to 3 weeks of the year for reaching your heating loads? And that is a question for your individual clients. Now, if we look at the same model, same type of systems in the mainland, so we have a mainland chill. We have a mainland, we have a, Langley, I'll say Langley. We have a Langley house, coldest day, 2.5% is about -15. That's the coldest day of the year. And then if we use the same heat pump in the same system, we meet that. We will not need supplemental heat. It will never be a requirement. So putting a system in with a heat pump in the lower mainland area with a lower end heat pump, now it doesn't even have to be good, seems pretty silly when you look at the math in terms of your returns and how much electricity costs with a heat pump versus natural gas. So when is a hybrid system viable? That's a good question. So relative cost of heating. Okay, so if we look at a heat pump, the relative costs associated that come with it. We have our electricity hookup, right? So everybody has electricity hookup, whether or not you use gas only on all your systems or not, you still need lights. You still need to run your base loads. You still have electricity hookup. And then you have your electricity usage, okay? That also comes with with any system. If we look at a heat pump with a natural gas furnace, you still have the electricity usage and hookup costs, but now you're adding a natural gas connection cost. This is not solely in the building phase, but this is on an ongoing monthly cost. Your connection cost is monthly, whether or not you use any gas or no gas. So then your natural gas usage, it's really low. And in fact, if you're in the lower mainland, I would suggest it's pretty much nil, unless you're using it for cooking and other sources. And then if we look at a heat pump with a boiler, and this is specifically with radiant heat, I'm bringing this up because radiant heat, as we begin to build higher performance buildings, it is less and less and less useful. It comes on so infrequently that you will not get your warm floor feeling, your warm feet. You will not have that for almost, well, in the lower mainland, almost 100% of the time. If you have your so if we look at the energy and relative costs, again, we have our electricity usage and cost hookup. Again, the same for every house. You need it no matter what. But then we have our natural gas connection for that boiler, which is which is similar to your furnace. But then the usage goes up drastically. And if you think about this, the reason for this is because the system is so much larger. Heating water in particular, you'll never have 100%. Your max is about 95%. And then you also have a large amount of water that you're heating for that 1 to 2 weeks to 3 weeks of the year, or maybe not at all, depending on where you live. Those are big costs that are associated with a system that you'll relatively not be using. And then there's other costs that come with this. Maintenance. So you have electricity, you have electrical systems. The maintenance costs on those are relatively low. You also have a lot higher life out of them typically. Your maintenance costs for a furnace, it just adds a whole other realm to it. I would suggest that this is at least double your maintenance costs. Typically furnaces, natural gas furnaces, boilers, anything like that have a 7 to 10 year life cycle before needing replacing. And then if we look at the boiler system, the maintenance is even greater. You may not think that you might have to do any maintenance to the actual system in the flooring or whatever, but this is false. Maintenance is definitely needed. And also, if there is a problem with the actual system within the flooring, that cost drastically jumps. So you can imagine having to chip out anything to get to it. And then again, just as a reminder, to June 2030, all new space and water heating will need to be 100% efficient. So a heat pump is 100% or greater in efficiency. Your air pump and natural gas furnace hookup, that is better than 100% efficiency. This as well is better than your 100% efficiency because you're hooked up with a heat pump. Now, I bring this up for two very, very, very good reasons. If you were to install this system without the heat pump, and then in 10 years, you needed to then get your system to 100%, you can't just throw in a heat pump unless you have designed the system beforehand to incorporate it with your natural gas system. So this upgrade becomes very, very expensive. Again, also, this is water heating as well. So if you go with a natural gas boiler for radiant heat and use it as a combi boiler, you will then have more than 100% efficiency. But if you have a boiler for only water heating, in the future, you will be replacing that with an electric tank. It's also my experience and many other builders' experience, and this may, well, I'm sure it's similar from your area, but the installation and the running cost of an electric tank is far less than a boiler or even a natural gas tank. This is so very true. So let's move on. So when is a hybrid system practical, you may ask then? Why are they becoming the big rage and all on the front pages of every individual HJ's websites? And the first and foremost would be in northern cold climates, where you have very cold areas and or cold extended areas. Now this is becoming less and less of a concern as cold climate heat pump technology is coming on fast. In fact, in the last 5 years, some of our cold climate heat pumps 5 years ago are now in the mainstream as just regular heat pump specifications. Older or leaky homes. But now this is also becoming a less and less issue as we move towards higher performance building. And it should be a non-issue for new homes. We shouldn't have leaky homes anymore. We're building to at least a 2.5 air exchange rate, if not better. So the leaky home is not really an excuse for new homes. And people who love gas and like to waste money. Now this is as much funny as it is, meant to show that people like comfort, and some people like to have the comfort of gas in their home, no matter what. Maybe they come from Alberta, maybe they worked in the oil and gas industry, I don't know. But some people do have a love for gas and a comfort for it, and that's hard to get around. But with some logical talks showing the cost savings, this can be a relatively easy conversation. It doesn't have to be heated or contentious in any way. Okay, I'm going to look at a few very generic examples here. Okay, so this would be, I modeled these homes all as if they were in Langley. Now this is a simple single family home, relatively small. This home only met EL2 and reached a step code of 3. You can see it's a pretty typical build for the mainland. R40 ceilings, 16-inch center, R22 in the walls, no slab insulation. Now they only did a 2.5 air exchanges because they only had to meet step 3. So this house here falls right here as its base. So as we said, it's EL2, step 3. Now to get it to the minimum of EL4 in the Langley area, you just have to increase the ACH to 1.5. That is all that's necessary. You can still have a full gas system. If you wanted to get into the new EL3 requirement of next year, you just have to turn that air conditioner. Oh, I should show that. We had an air conditioner here. Tisk, tisk, never install air conditioners. It's silly anymore. Air conditioner just needs to be replaced to a heat pump, and now you satisfy the EL3. So basically, you just had to increase the air exchanges, or decrease them, I should say, but improve them, and change to a heat pump, and you're meeting that EL3. Going to EL4, you just have to change to a dual fuel system or all electric. Okay. Okay, and then this is a large single family home. This is very large. This is very typical of a house that you do not want to design for. Very many corners. This is not a high performance designed building. You can see that they had to put R24 in the walls, full slab insulation. We have R50 in the trusses and in the roofs. And then again, AC, but this one also has a gas boiler, okay, for radiant heat. Now this home, step 3 minimum, and it only is measure only, EL1, very brutal. Okay, so just to get to to get to step 4, all you'd have to decrease the ACH to 1.5, the requirement, put in a low end heat pump. So this does not have to be a Mitsubishi or anything like that. It can be something off brand, Rheem, whatever. And then a gas boiler can remain for in-floor heating. But you change the dual fuel here. To get to EL2, basically it's the same, right? So you can see step 3 and step 4, the ELs are in step 2, right? So step 4, you move to step 4, and you're automatically in EL3. EL2, my apologies. EL3, all you have to do is then, again, nothing. You're already in EL3. Again, back to that original slide where you sometimes fall into EL3 by accident. This is one of those cases. To get to EL4, you then have to put in your electric hot water. Okay, so this is gas hot water, electric hot water. That's the only difference to get to EL4. This is pretty significant because I think everyone is very afraid of the EL4, EL3, but they're very similar. And then typically you are already at an electric hot water system in this area because it is cheaper to switch over than anything. Now the step 5 upgrade package here is robust. You have an ACH of very small. And this is, again, because the design of this house is not for high performance, right? The pool, not counted. Neither is the heated driveway or the shop. Townplex, okay, or sorry, fourplex, townhome. Relatively straightforward. Again, EL3, step 3, EL3. Similar designing, similar assemblies as the single family. Small units with higher surface area often have problems with the MUI. The TEDI passes easily, typically in these ones. And this is because you essentially get rid of a wall. And in the middle units, you get rid of 2 walls because they're conditioned on both sides. So the TEDI will pass easily. The upgrades are typically for the MUI in this situation. So with that townhome, it meets EL3 at its base, right? No changes required at all, meets step 3. To get to step 4, you just have to increase the performance of your air tightness to 1.5, which is the requirement for step 4 anyway. To get that step 4 house into an EL4 situation, there's my pointer, all you have to do is install a low-end heat pump, and this townplex is now EL4. Very minimal upgrades. Your step 5 package upgrade is pretty small. So they went into a high-end cold climate heat pump and a hot water tank, or heat pump hot water tank. Last one is a small house. I bring this up. go to the next slide, but small house, EL3, it meets EL4 already as designed. So it has some full slab insulation. Windows, again, not particularly high. ACH is 2.5. Now, the difference here is this is an electric system. I imagine they went with electric because it's relatively small space and, well, it'd be relatively easy to maintain, and the cost would be significantly lower for install. Now, this meets EL4 without any changes, and that's because we were all at an all-electric system, right? To get to step 4 with this project, all I was needed was to increase your ACH, your air tightness performance, to 2.4. Now, this might sound funny because we know that the requirement for step 4 is 1.5, but there is also, and I hope this was covered in your last meeting, or maybe hopefully you all know this, but the new metrics also allow for your normalized leakage area to be used. So this is very relevant in small homes because you can imagine it doesn't take very long for the entire volume of this house to leak out compared to a small single family home. So we use normalized leakage area. So that falls, so all that was needed, didn't even need to change your air tightness in this regard. All was needed was a low end heat pump to satisfy that. And then to get into step 5, you just needed small increases. So R40 in the bat, I think that was the same. R22 in the wall, same. 1.4 windows, so a very small increase in performance. And your cold climate heat pump was used to get into step 5. And then they used an ACH of 1.6. So the NLA was used, again, same situation. So key takeaways from here, basically, these homes at step 3 took very minimal changes to get to step 4. Also minimal changes to reach the EL3 if it wasn't already fallen into that. It's the zero carbon step code is a false sense of advertisement. It is not zero in any way. So those people who do have a comfort and want their gas, it does not mean you do not need it. You cannot have it. Also is relatively easy to get to step EL3 and EL4 with very simple upgrades. And then where do you find trades who all know how to install this stuff? Please visit the HPSC. They're a very good resource for this. And that's all I have for me.
Thank you so much, Tom. Yeah, so this has been a very interesting session. Now, and thank you for doing it right on time. We got 2 minutes to spare, so we got time for questions. And so before we get into that, it's we have posted a link of our survey. Like this is how we can justify the resources that we spend on these putting up similar free events. So please complete the survey, and this is how we will know how we did, and your feedback is really important for us. And I would also like to thank Kira and Kevin for supporting us in hosting this one. And Tom and Todd, thanks a lot. There's lots of useful information in your presentation. Please note that this is a recorded event. It will be posted on our on-demand learning portal. Kira will be posting a link so that you can access it, and also make sure you can get credits. So it's not like you're just watching some video. You can also earn credits. You're learning and you can earn. So that's it, and we are open to questions. I know we are at time, so if anybody want to leave, please go ahead, and you can leave. Otherwise, if you'd like to stick around for some time, Tom and Todd will be answering a few questions. Tom, so there's this one question from Nicholas. Hi, Tom. On-demand electric hot water heaters useful for small dwelling units, or is electric storage tank better? You're muted.
Sorry, could you repeat that? I missed the very first part.
So on-demand electric hot water heaters, are they useful for small dwelling units, or is electric storage tanks better?
That's a good question. In our experience, the electric water tank, the conserver tank, is the least expensive to install because you don't need gas hookup for one. And you just need basically an electrician to hook it up. And then the monthly costs are relatively low as well. So I would suggest the hot water tank, especially for a small unit.
Okay. Anybody, if they have any more questions? Okay. Okay, I think this is not a question. Yeah, people love radiant heat and are willing to spend 50K for it. Concrete pour, exterior insulation, and triple pane windows just for getting step 5 compliance. How have you convinced your clients to walk away from it?
Well, it's a tricky conversation, to tell you the truth. A lot of people come into these conversations with preconceived notions of what's going on. Yes, we are going to have, and we will continue to have, people who love their gas, who love their radiant heat, and who will want it. I try to show the numbers, and I try to show the fact that radiant heat in high performance building rarely comes on. I have had people say, I will just install the heat pump and turn it off in the winters, just so that they will have that heated floor and warm floor feeling. That is all totally up to you. That is a client perspective. I would caution on it, and I would recommend to do your own test. If you have a heat pump and you have radiant in-floor heating, turn your heat pump off for 1 month in the coldest part of the year and compare it to with your heat pump and see what's cheaper. I have a I suspect highly that it will be the heat pump.
Okay. I think, people have been keeping Todd really busy. Yeah. So and thank you for that. This is the idea of this forum. We want to have these conversations. Todd, if you have any questions that you would like to answer, you can go ahead and do that.
Okay, I'm typing out another like half a pager here,
Yeah.
and I'll see I'll see if they're ready after that. So bear with me just one moment.
So here's a question from Matt. Yeah. Can you share where the number of buildings meeting certain step or EL level was obtained from? Is this the provincial data?
Yes, so all that data I had is from CHBA BC. So it's all new buildings that have happened since 2020. Yeah, so the last 4 years. So it's all of BC's new buildings.
Okay, so with that, we are at 11:04. So I would say, if there are any questions that we haven't responded to, we will be putting them in a chat. We'll be putting a Q&A document after the event on our Green Buildings on Demand page. So we recommend you can visit our page, sign up for that. You can also watch our previous events and earn credits. With that, I would say thank you. Thank you.
Oh, Ajeen, I did see one question earlier, and I'm not sure if it was answered. So one question was about load sharing,
Right.
and load calculations with it. And they're asking, if I remember correctly, why and when are we allowed to not include EV chargers in load calculations? And in that example that was shown, in BC Hydro example, what happened there was that the EV charger was being shared with the stove, with your electric stove. So when you do your load calculations for that, you do it with the highest load of the two, which generally would be a stove. So then you do your load calculations with the stove in there and not with the EV. And the only reason you're not including EV is because it is only coming on when the stove is not working.
Okay, thank you.
All right. Thanks, everybody.
There is also one other thing to consider. There is a pathway where if you have, I believe it's 1 year's worth of data from your utility company, you can show that you can use the actual load, peak load, plus I think 25%, and use that instead of the prescribed watts per square foot.
Yeah, that would work well in retrofit situations.
Yes. In some cases, that can be just enough to bring you down into not requiring servicing or a panel or a service increase. So I believe it was in the CEC section 8.
Yeah, and I believe that's for retrofits you can use historical data.
Yes.
Now I want to place a large caution on that. If you do upgrades and retrofits, your loads may change.
Absolutely.
So take that with a grain of salt, because if your house becomes much more efficient, you'll need less load. So
you also need a professional or a certified person to conduct that analysis too.
That's right.
That's not something you can just throw in a spreadsheet and I'm off to the races.
That's right.
Okay, thank you so much. That was
Thanks,
a lot
everyone.
of conversation. Yeah, just one
Thanks,
last
everybody.
note, just one last note. Your credits will be sent to you by email as a receipt, and you will have to self-report it, except for AIBC. For AIBC, the registration name and email address will be used for, and we will be sending it to AIBC. Thank you.
Have a good day.
Thanks, everybody.
Bye.
Have a great day. Bye.